We'll get started now, so please get settled in. Good morning, everyone, and welcome to our third day of Data Week. I'm really happy today to introduce our keynote speaker, Professor Marilyn Walker. Marilyn is a professor of computer science and engineering at the University of California in Santa Cruz. Unfortunately, she couldn't drive up here today, but we will have her on VC. She is the chair of the Natural Language Processing Master of Science Computer Science program at the University of California. And she's also the director of Natural Language and Dialogue Systems Lab at UCSC. Her career spans both industry research and academia as well. She has previously been at the University of Sheffield before she joined Santa Cruz. And previous to that, she was at various research labs like AT&T Bell Labs, Mitsubishi Research, and Hewlett-Packard as well. She has made pioneering contributions in the area of statistical methods for dialogue optimization and natural language generation. And she was inducted as a fellow of the Association of Computational Linguistics in 2016. Today, she will be talking about her work in controllable neural natural language generation for open domain spoken dialogue systems. As you know, natural language processing is of great interest to LinkedIn, and I'm sure this talk is going to be really exciting. Please add your questions to the Slido link. The Slido link is in the Outlook invite, and it'll also be in the Zoom chat. And please upvote questions that you like. So without further ado, I'm going to turn it over to Lynn. Welcome.
Hi, thank you, Anant. Thanks for the introduction, and thanks everybody for inviting me today. I'm going to present some recent work with my students at UCSC on controllable neural natural language generation for spoken dialogue systems. And first, I'm just going to set a little bit of context for this work. Watch this not work. Okay, there. Oh, I got to set my stopwatch. Okay, so I just wanted to start off by saying that I've been interested in natural language generation for a very long time. I started doing work in this area in the context of spoken dialogue systems at AT&T around 2000. We did work in this area for DARPA Communicator Project, which was a big multi-site spoken dialogue project funded by DARPA. And, you know, I started work in this area. Nobody was using natural language generation for dialogue at that time. And, you know, started work in this area by developing an architecture and methods for training statistical natural language generations for dialogue. And so my first publication in this area was 20 years ago, in 2002. And that's when statistical NLG was just taking off. And my team did some of the very first work on NLG for dialogue systems. We also worked on many different aspects of stylistic variation for dialogue. And I still think that this is, of all the things I've done, this is the thing I'm still most interested in, this controllable dialogue generation. So a lot of the work in my lab using neural models recently has focused on testing whether we could do the same kinds of things with neural models that we could do with statistical NLG. And obviously, well, it's obvious to me, the statistical NLG is much more controllable. You know, we have this issue with some of the neural models where it's a little bit hard to figure out what's going inside that black box and how to make it better. And I think you'll see that in this talk. So I want to make it clear that our setting for controllable NLG is for situations where we want to generate a conversational style utterance for some kind of factual information in a dialogue setting. For example, in the video games domain, you might have an input, an utterance from the user, such as, have you heard of the game, The Legend of Zelda? And this utterance gets fed to natural language understanding engine, which, among other things, contains a module for named entity recognition and named entity linking. This module identifies the named entities and it links them to the Wikidata knowledge graph or another database, like the video games database. It then passes this information along with other natural language understanding results to the dialogue manager, who then decides what dialogue act to generate in the given context. And in this case, it would be an informed dialogue act with a selection of attributes and values that the system wants to say, such as the release year, the developer, and the genres of the game. And then we generate a user response. The Legend of Zelda: Ocarina of Time is a role-playing action adventure and puzzle game that's both third person and bird view. It was rated E for everyone and was developed by Nintendo EAD, and it was released in 1998. So here we've highlighted in color the correspondence between the output utterance and the meaning representation that was given. And generally the goal here is to make sure that you generate each and every one of these facts or attribute values. You generate each and every one of them once and only once, which is sometimes a challenge for neural systems. So what's important to keep in mind about meaning to text generation for spoken dialogue is that you want to control the semantic meaning. You have something in particular that you want to convey. You're not just trying to say something that contributes to the conversation. Also, we want natural conversational style. We don't want the system to sound like it's reading Wikipedia out loud. And sometimes you might want to control the sentence structure, the style, or the personality, depending on the setting. In the past, typically you needed large crowdsourced data sets to do this, and getting these can be expensive. They also may not exhibit the style you want. And it's well known that the crowdsourced training data can have a lot of quality issues. So in this context, we've explored controllable NLG for controlling both semantics and style. And there's lots of different methods and models for doing this. It's a very active area of research. Ananth asked me to skim over some of the technical details on this. I'm trying to do that, not spend too much time diving down into what exactly these models look like. People have used both LSTMs with attention and transformers. They've directly trained off of a big corpus of dialogue, or they've tuned from a pre-trained large language model. There's a couple of different strategies. One that I'm going to talk about is conditioning on constraints in the input. And there's also more recent work on prefix tuning and prompt tuning in this area. And I'm going to talk in more detail about two of these methods. I'm not giving an overview of all the different methods. So I'm going to talk a little bit about two different projects, both of which avoid the need for crowdsourcing a large data set. The first project, we're going to control both semantics and style using an LSTM plus attention architecture with these input constraints. And we're going to train a restaurant natural language generator using naturally occurring restaurant reviews. And the second set of experiments, we're only going to experiment on semantic control, but we're going to do that with few-shot prompt-based learning. And we conducted a lot of experiments across these 5 domains: movies, music, sports, TV, and video games. And we trained and tested both within and across domain. So let's just get onto the first one, which is where we trained in NLG with Yelp restaurant reviews. And this is the thesis work of my student Shireen Orabi, who now works at Amazon AI on conversational dialogue. So one of the first things that we observed is that social language in the wild is very highly expressive, and you never, current natural language generation engines never will produce anything that would be this expressive, this huge richness and complexity of style choices. You never see this in crowdsourced data. So for example, if you look at this positive review here, you can see what's known in the linguistic literature as hyperbole, with phrases like "the best I've ever had," "that stuff changed my life," and "ridiculously delicious." If you look at a negative restaurant review, you get the same thing, but with these very strong negative hyperbole, like "I want to curse everyone that I know," "it's absurdly overpriced," "princely sum," and brand new words like craptacular. So the question that this work asks is, can we use this real user-generated content to train a neural NLG engine? And one of our prime motivations is to avoid crowdsourcing data, but also we're really interested in the fact that this language is much more interesting and descriptive. And also crowdsourced data comes with user ratings, which can be used as sentiment labels for the data, like in many other corpora, like the IMDb movies corpora or Amazon reviews. So this work, as I said, it uses an LSTM plus attention architecture. It doesn't use a pre-trained language model. We created this huge corpus of 300,000 instances mined from the restaurant reviews. And we did this work in one framework for controllable natural language generation, where the meaning representation is a flattened set of attribute value pairs. And so if you were just generating using only semantic control, you might get something like this. Brown's Cambridge is near Crowne Plaza Hotel. Brown's Cambridge has a 3-star rating, and it's a family coffee shop. But one of the common ways to introduce stylistic control is to introduce into the input meaning representation some kind of constraint with a value or a set of constraints and values, and then you would get a constraint stylized output realization from having training data that has this constraint marked up. So for example, we have a large corpus that's labeled with personality attributes. So if we add this personality unconscientious to the training data and we give it training instances for unconscientious stylistic output, we then would be able to produce personality unconscientious at generation time. And this is an example of some of the things that unconscientious personality people are supposed to do. Say things like, oh God, I don't know. They're supposed to produce really long sentences, use hedges like. So that, that would be an example of this controllable meaning to text NLG by using these constraints, also called side conditions, token supervision. There's a bunch of different names for this. So what we want to do is we want to generate for meaning representations, but obviously a corpus of user reviews don't automatically come with meaning representations. So what we're going to do in this case is we're going to create these conditioning markups by doing what we call retrofitting of meaning representations. And I'll explain this in a lot of detail. We automatically add multiple stylistic conditioning tokens as well. And we experiment with different levels of representation. So we're going to experiment with having, one small set of conditioning tokens and then add more conditioning tokens and more so that we can see what happens to the output when we select particular conditioning tokens or control variables. So these experiments are aimed at identifying the control variables, however many there might be, both semantic and stylistic, that will produce semantic correct, but also expressive output that takes advantage of the natural expressivity in the corpus. So to retrofit the meaning representations, we first note that sentences discuss a lot of attributes of interest in reviews. They talk about the food, different kinds of food type. They talk about the wait staff. They talk about the type of restaurant, that it's a chain restaurant. And they also use lots of adjectives like tender and juicy, okay, a little bit dry. So we get this kind of markup, and we can generate this markup. We can generate this markup automatically by using large gazetteers that we scrape from DBpedia and other sources. So we can start off, we mark up things via the gazetteers, and then we parse the sentences. And that helps us identify the adjectives that are in the sentences because they're marked with the part of speech tag, for example, JJ. Also, what we do is we, if we have an entity in the, and a gazetteer like meat, and it gets parsed as a noun-noun compound, we introduce a new lexical term for this, for tender meat. So this isn't maybe not exactly what you want, but what this is saying is that tender meat is a particular lexical item itself, and it's inferred that from the parse. Also, this one doesn't look as good, but you see it does the right thing here for hoisin sauce. So it knows that sauce is an entry in a gazetteer for a food type. It may not have known hoisin before, but the fact that it's a noun-noun compound the system infers that hoisin sauce is a particular kind of food entity. So, and then we also add stylistic control tokens, and these are pretty simple and straightforward in these experiments. We tag these other sentence level style attributes. So we copy down the sentiment from the original review. We calculate a length bin, how long the sentence is. We introduce Boolean markups for whether the sentence has first person pronoun in it, whether it ends with an explanation. And we keep track of mentions because the same attribute can occur multiple times. So what we produce for a sentence like this is that, you know, there's an attribute of the food type and its value is tender meat. There was no adjective applied to tender meat. And this is the first mention of that particular kind of attribute. Then we have the duck, and we have an adjective perfect. And this is also the first mention of duck. We have an attribute for scallion, and it didn't have any adjective at all, and it's also the first mention. And we have an attribute for food whose value is, that's a typo, hoisin sauce, with the adjective little, and again, the first mention. And then we copy down the sentiment from the review, which was positive. This happens to be a long sentence in the long bin. There's no first person in here, and there was no exclamation. So let's just go quickly through a few more examples so you get the idea here. So if you have a sentence like the food was pretty good, I had a chicken wrap, but the service was crazy slow. We have the different kinds of, we have a food attribute for the chicken wrap, which didn't have any kind of specific adjective, and it was the first mention. And we have another attribute for service, which we see was slow. We missed the crazy there. And the sentiment was neutral in this review, which means it was a 3. The length bin here is medium. It does have a first person pronoun in it. I had the chicken wrap and there was no exclamation. This example shows how the mention comes in. It helps to associate, these mention attributes help to associate the right adjective with the right food type. So here chicken is mentioned 3 different times: bland chicken, spicy chicken, well-seasoned chicken. And by keeping track of these mentions, mention 1, mention 2, and mention 3, we can distinguish between these 3 noun phrases that are mentioned. Again, here we get central sentiment is neutral, length is medium. In this case, there is a first person and there's no exclamation. And similar, this one illustrates this noun compound thing. Again, we infer that beef chicken kebabs is a particular kind of food entity. And then it's we get the adjective succulent here. We get the adjective buttered for the rice, buttered rice, and broiled tomatoes and raw onions. So we get all these adjectives here, and we have a positive sentiment. It's long, it doesn't have a first person, and the exclamation is false. So as I mentioned, data sets are usually large and costly to collect. And when we generated this database in 2019, it was the largest next to Wikibio. And therefore, as I said, we did direct training with this. We didn't use any pre-tuned language model. And I just want to stop for a second that this might all seem really straightforward, but there were many reasons why we thought it might not work. One of the main reasons is that it's quite a weak semantic representation. There's a lot going on in these sentences that is not actually represented in the markup that we generate. And so it's interesting that because we have such a huge corpus of 300,000, with the smoothing with these control variables, we actually do get very good semantic control because the model seems to learn to ignore all the stuff that's not marked up. So let's look just at what these experiments did. As I mentioned, we have different levels of representation and we steadily add more condition variables to see what the differences are in the output. So the one that we call our base representation just covers the things here in bold. just the food attributes and their values, and it doesn't include any of the adjectives or the mentions or the stylistic markup. So when you evaluate what you get with the base, you actually get something pretty good, but it's specifying adjectives that aren't actually the ones that were in the original sentence. And you get the semantics right. It actually mentions the porridge, the meat, and the flavor and the soup, but it doesn't get the sentiment right because it wasn't told to control the sentiment. It doesn't get the length right. It didn't get any information about what length it was trying to achieve. It does by accident get the first person right, and it does by accident get the exclamation right. When we add in the adjectives, we get, so the porridge didn't have any adjective, but the flavor of the soup was rich. So we get this flavor rich adjective there. And because adjectives carry a lot of sentiment, without specifying sentiment, we actually do hit a sentiment target. And again, the first person, the exclamation are okay. When we add in the sentiment, we can see that it emphasizes the sentiment a bit more. So it expands this positive phrase from rich to rich and delicious. So it kind of makes sure it hits the sentiment correctly. And then when we add the style parameters, which are that it's supposed to be positive sentiment, the length is long, first person is false, we actually get the longer sentence. It tries to fulfill this length parameter that we gave it here and produces something that's longer. And that simple control with making the length longer or shorter often has a lot to do with how flowery the language is, because it has to find some way of saying something that is longer than other ways of saying it. So we did a number of evaluations for this using both automatic metrics like BLEU, as well as a range of other metrics that we developed to measure stylistic differences. And here I just want to show that that it worked with a quick view of our human evaluation. As I said, we have a whole bunch of automated metrics that we also report on in the paper. So we ran this mechanical Turk study where we asked Turkers to judge the fluency and the naturalness, whether we get the sentiment right and whether we get the content preservation right. And this is what the mechanical Turk task would look like. We didn't tell people, obviously, what sentiment was specified here in question 2. We just asked them to rate the sentiment. And then the required content is shown here in red. They're supposed to make a judgment of whether the delicious chicken shawarma was actually realized in the output. And the results in this table show that as we add more constraints, the content preservation gets better. The base one obviously doesn't specify enough. If we add the adjectives, we do better, even though this isn't having to do with the content. Adding the adjectives help us get the content better. And adding the sentiment, that's also better than the base, and adding the stylistic parameters also help us do better than the base. There is error in the sentiment, but not a lot. It's less than 1 off. And the fluency is pretty good with the base, according to Mechanical Turker's judgment. Apparently, they don't think that it's as fluent when you get this more flowery language, but these differences aren't significant. So one of the things I really like about this is that, as we said, this original corpus is very large and it has a lot of expressive variation. So without actually specifying some of these things, which we have controlled in other work, we get them kind of automatically. We get other pronouns besides the first person one that we're controlling. We get contrastive sentences like this, but the chicken's a little on the dry side, but nothing to write home about. This probably occurs, like I said, if you specify that you want a long utterance, you're going to get more likely to get these more complex sentence structures. We get what's called aggregation in the natural language generation literature, where we combine different attributes or things that we want to say into a single sentence using phrases like both of which, and, or long lists. And our results show that we had really good control of the adjectives. These are the first experiments that we know of using a neural method to do lexical selection. So the adjective specification worked really well, and we get a lot of adjectives and really good control of them. Okay, so that's pretty good. I'm about half done, and that was one set of experiments. So we trained an NLG that can take advantage of expressive language and other stylistic variation in naturally occurring restaurant reviews. We didn't need to crowdsource a large data set. We could take advantage of what was already there, found data, and we show that it's possible to simultaneously control the semantics and the style with fully automatic markup of the meaning. And we showed that the more control variables we use, the greater variation we get in the outputs. And I have more slides in the extra slides later if anybody wants to follow up with questions about this. But right now, Ananth, is it okay if I go on to the second part of the talk and leave all the questions till later?
Yeah, sure.
Okay. So as I said, I'm going to talk about two projects. I just finished this one where we tried to control both semantics and style. And in this second project, we're just going to experiment with semantic control using a newer paradigm of prompt-based learning, few-shot learning. And we did experiments with the movies, music, sports, TV, and video games domains. And we experimented by training and testing within a domain, and also training in one domain and testing in another domain. So these experiments were done in the context of our Athena open domain dialogue system for the Alexa Prize. Athena can talk about, these are the different topics that it has information about. It can talk about TV, movies, music, animals, sports, comic books, Harry Potter, nature, all these different kinds of things. And some of these topics are, the content is populated from the Wikidata knowledge base, knowledge graph. So in these experiments, I'm going to focus on these particular topics, movie, music, TV, and sports, which are where the content comes from a knowledge graph. We also have another meaning to text generator that we experimented with in this few-shot prompt-based learning paradigm for the video games, but I don't have that included in the main part of the talk, again, because I'm trying to meet the 45-minute time constraint. And we did these experiments last year, and published them in the International Workshop on Spoken Language Technology, which was held in early November. So just let's have another example of how the meaning representation here differs a little bit from the example that I showed for the video games. So let's take in the music knowledge graph response generator, let's say that the system asks the user, do you have a favorite musician? And the user says, yeah, Taylor Swift. Again, we have the natural language understanding, which includes the named entity recognition and named entity linking. And it links Taylor Swift to a particular Wikidata ID. And then that gets passed to the dialogue manager along with some other natural language understanding results, not just the named entity. And the dialogue manager selects particular triples that it wants to say about Taylor Swift. So in this example, it wants to say something about how many tracks Taylor Swift has produced, and it wants to talk about her song called 22, which came out in 2013. And so that gets passed to the natural language generator, and it attempts to produce something that's very natural and conversational. So it says, okay, Taylor Swift, wow, she's very prolific. She has 114 songs. I like her song 22 that came out in 2013. So the difference in this example from the video example that I showed earlier is that this, we have sets of triples that are passed in for the meaning that look kind of like this. And you can have any number of triples from just one triple up to 4 or 5 triples. And we don't have any dialogue acts with this. We're just passing these triples. We haven't specifically used dialogue acts in these response generators. So here's a few examples. If you have, a triple like Wonder Woman's director was Patty Jenkins, this would be an example of something that the response generator would produce. I believe that Wonder Woman is directed by Patty Jenkins, and then it produces these other kinds of utterances that kind of pad it. They don't directly come from the knowledge graph. And this is what the training data looks like. This is what that response generator actually produces. And these responses are generated by template-based generation. And what we wanted to do in these experiments was to take this synthetic data that's produced by template-based generation and use it to train a neural NLG engine that hopefully would generalize much better to new domains and new relations. So here's another example. Taylor Swift plays electropop, like the song Blank Space. Do you like that genre? And that has two knowledge triples, Blank Space, performers Taylor Swift, and its genre is electropop. So I think you kind of get the idea there. Now, what we're going to do here is use prompt-based learning, which is a new few-shot learning paradigm. This is based on Radford and Brown's work, where Brown et al. Showed with GPT-3 that you could do this context conditioning, and prompt-based learning is a particular kind of context conditioning where you give examples of the particular task that you want the language model to do and then prompt it. And I'm going to show you. So you condition the model with these end prompts. Important thing to notice is that you're not training any parameters. So normally with fine tuning, you take the parameters originally in the language model and you tune them to your particular task. Here, the only way that you do any kind of tuning, if you want to call it that, is with these prompts. And there's been pretty small amount of work on meaning to text generation using prompt-based learning. It's very active. It's a very active area. This work by Li and Liang on prefix tuning actually works on meaning to text generation. But at the time that we did this work, we weren't familiar with that. So this is a little bit different than what we did anyway, but there's been very little work. When we produced our paper, we thought we were the first people, and I really don't know in terms of when it was in 2021 who was first with this. So we take two pretty large pre-trained language models, but our baseline model is a smaller one. It's like GPT small. It's a transformer-based language model. It has 1.7 billion parameters. And for its size on some kind of standard tests like GLUE, it's been shown to perform quite well. And then Jurassic 1 is also a transformer-based language model, but it has 178 billion parameters. And it's been shown to achieve state-of-the-art performance on a set of common sense and QA zero-shot and few-shot tasks. So this, the people that produced Jurassic 1 Jumbo set out to have it be the same size as GPT-3, but they experimented with some of the parameters like the width and depth of the network that you can read about in this paper, Jurassic 1 Technical Details and Evaluation. So based on these two pre-existing large language models, we create what we call Athena GPT Neo and Athena Jurassic by using prompt conditioning to generate the desired output. So we created prompts using Athena responses for the Wikidata knowledge triples. We have tons of those because it's synthetic data. So we had all this data we didn't need to use. We had over 32,000 knowledge triples and their responses. And we focused on these 4 domains: movie, music, sports, and television. We created 2 different test sets. We have an in-domain test sets that's 100 instances from each template category within the training data. So they tend to look like the training data. And then we, by hand, we looked at the knowledge graph and we created 100 relation combinations or introduced entities which were not in the training data. Because what we're interested here is generalization to unseen relations or entities. And because our initial models use template-based generations, basically for every relation combination, you'd have to write a new template. So you don't write templates for rarely occurring relations or rarely occurring entities, because you might have very little opportunity to actually use those in the system. And what we wanted to see here is if we could get out of that bind of having to handcraft these templates by using our synthetic data to train a neural network, and then hopefully it would generalize well to unseen relations. So that's the point of this novel test set. So we did more experiments really than I can talk about today. As I said, we did experiments both within and across domain. I'm just going to talk about the within domain experiments, and I'm going to talk about this novel test set, these unseen relations and entities. We experimented with multiple prompt formats. I'm only going to talk about one of them. And I don't have time to talk about the experiments that we did in the video game domain, but those, the meaning representations in the video game actually has 9 different dialogue acts. And we did a lot of experiments on whether we can control the dialogue act realization, and we're still doing additional experiments on that now that we're hoping to wrap up in the next month or so. So the S2S sequence to sequence prompt format, it flattens the meaning representations of the triples. It represents the triples like this, and then uses a separator, and then concats the other triple. And so what you do in this prompt-based method is you give, this is the same as, Brown et al. 20, you give a few examples of the task that you want the system to do, that you want the language model to do. Like this is one example in the music domain, and here's another example in the movie domain. And you again, you give an example of what you want the output to be. And then what you do is you give the input, but not the output. And what you want to, what you're judging as this is a test item. What you're judging is how well the model produces that output just based on a couple of examples. And so one thing to notice here, and this is what we did in our few shot novel experiments, is here we just have two examples. One of them is in the music domain, one is in the music domain, in the movie domain. And then we have an example here from the movie domain, but I'm going to show you later on. We also just use these exact same 2 prompts in the music and movie domain, and we actually tested it on things like television and sports. So if you look at what the output is with Jurassic 1 with a temperature of 0.7, we use 0.7 because we wanted it to generate more variations. We get these, we can get 3 or more. Obviously, you can get as many as you want. The Audrey Hepburn won the Academy Award for Best Actress in '54 for the movie Roman Holiday, right? So that's all there. And then it adds a question by itself, because some of the training data actually includes these questions, and we don't have a way right now to control that. This one doesn't have the question. This one changes the order around and talks about the Academy Award first, and uses this, passive construction. Academy Award for Best Actress was won in '54 by Audrey Hepburn. So the model produces a lot of variation, and you can see that all 3 of these are semantically correct. So we ran experiments, as I said, across these 4 different domains using triples from Wikipedia: movies, music, TV, and sports. And these are just a few of the examples. So this is with GPT-Neo, which is said is 10 times smaller than Jurassic. And you can see that it produces quite fluent output right here. But actually it's got semantic errors because it doesn't say that it's the 47th BAFTA, and the 47th BAFTA did not occur in 1980, it occurred in 1994. Also, you can see that this smaller language model, it says it knows stuff about Kelly Pickler. So it actually says that she's a country singer, which isn't specified here, and also a rapper. And then it adds this question about her. It doesn't say that her song is Red High Heels. It does say that she's a country singer, but it doesn't say that Red High Heels is country music. And the Athena Jurassic, as you'll see with our quantitative measures, actually gets much higher semantic accuracy than the smaller model. So our evaluation metrics is that we use BLERT, which is a BERT embedding based version of BLUE that allows you to get more at semantic meaning, a little bit more at semantic meaning than BLUE does by generalizing over word embeddings. And then we did a lot of human evaluation because we didn't really trust BLERT. We wanted to do the human evaluation so we could actually judge whether BLERT was useful or not. And so with the human evaluation, we marked the coherence of the utterance with a score of 1 to 3. We calculated the semantic accuracy so we could automatically count how many triples were in or attributes were in the meaning representation, but then we checked by hand whether those were all realized in the utterances. And we kept track of hallucinations, which is a hallucination is something like Kelly Pickler is a rapper, which is not specified in the meaning representation. And what this required us to do is actually look up whether Kelly Smith is a rapper if we didn't already know. And if she is a rapper, we would say it's a good hallucination because it actually happened to be true extra information. And if she's not a rapper, we would label this as a bad hallucination. And then we kept track of whether or not a question was added to the end of the candidate, because as I said, these particular meaning representations don't have dialogue at control. So we're interested in seeing how much it happened that a question was added. So for these automatic metrics for the 10-shot, we use 10-shot prompting. So we have 10 movies examples, and then we generate for movies or 10 movie examples. And then we see how we did generating for music, TV, and sports. And so the within domain results are across the diagonal here. And this is the Jurassic result, and these are with the GPT Neo. So one of the interesting things here is that you can see, as I'm not going to really talk much about cross-domain, but you can see here that sometimes the cross-domain result is as good as the within-domain result, which is quite interesting. I'd like us to have more time to kind of quantify this better. So the TV, it's interesting. If you train on TV, if you train on movies and test on TV, you actually do way better. The thing about BLERT that you might not realize and be wondering about these negative numbers is that it's a trained model, and the absolute numbers don't really mean anything. You have to use their relative values. But the other thing about this is if you look at it, these differences aren't statistically significant. If you just look at the BLERT score, it looks like BLERT and GPT Neo are doing just as well as each other. And as I said, part of what we were trying to do is figure out whether it was good or not to use BLERT. So we focused our evaluation on within domain here to do this, our semantic markup. And what this shows is that the coherence for GPT Neo is significantly lower than the coherence for Jurassic as judged by humans. The semantic accuracy is significantly lower. The number of hallucinations overall is significantly higher, even though some of the hallucinations are good. We have fewer hallucinations with Jurassic, and they both of the models add a lot of questions on the end without being told to. And so that's these are this within domain results. And then we had this novel rare relations test set that I talked about before, where the training is just the 2-shot examples that I showed, one for music and one for movies. And we use a lot of different, so these, this markup in bold are relations that we didn't have in the original training data. So you can see that we introduce a lot of relations or relation combinations that we didn't really have before, like that the Bechdel test is an assessment measure, or that Usain Bolt's rest time or a significant event. So these are the kind of things we introduce, as I said, in the novel set by like looking over the Wikipedia, Wikidata knowledge graph and seeing what relations that we thought were interesting that we could test. So I'm going to skip over the BLERT scores and just talk about the human metrics. So we have GPT-NEO up here and then Jurassic, and we get a drop from the within domain testing with 10 prompts, but Jurassic kind of holds up, to me, it holds up amazingly well. It gets a 2.8 for coherence, and its semantic accuracy is still at 0.72. Its bad hallucinations are kind of small, and most of the hallucinations that it produces are good. Whereas the semantic accuracy for GPT-NEO with just a 2-shot training and kind of some cross-domain testing really, really drops. And what you see actually in coherence, the reason that the coherence score ends up being so bad is it starts doing this repeating itself kind of thing that is really familiar to people that have done work on natural language generation, of getting these repetitive utterances where the model might say the same thing over and over again. So even though these results are not necessarily good enough to use in a live system, we were pretty amazed that this 2-shot training with these novel relations and some cross-domain testing actually did as well as this. So here's a few examples kind of going back to these where it, Jurassic actually gets the semantic content pretty well. Here, Peter O'Toole gets a David D. Donatello Award for Best Foreign Actor. It's never seen anything like that before for Best Foreign Actor. This Song of the Year relation at the 54th Annual Grammys is something it's never seen before. And the model decides by itself to talk about this rolling in the deep in a question like that. The model obviously has knowledge. Jurassic has a lot of embedded knowledge, like other people have talked about with these large language models. It introduces this good hallucination of why elementary passes the Bechdel test, this is basically a definition of the Bechdel test. At least 2 of the named women talk to each other about something other than a man. Here with the Usain Bolt example, it's interesting, it knows a lot. It talks about instead of saying what his race time was when he broke the record, it talks about what was the previous record before he broke that record. And then, another one is like significant event. Lighting the Olympic cauldron is a very rare event. Obviously, it only happens when the Olympics happen. So we would never write a template for that. But the output is absolutely correct that Muhammad Ali lit the Olympic cauldron at the 1996 Summer Olympics. So we're pretty excited about this potential that you can just take arbitrary sets of relations out of a knowledge graph and actually get the model to produce something coherent. Obviously, there needs, more work needs to be done. So, this work, I'm at 46 minutes, I have to hurry. Created new neural models, used 10-shot prompt conditioning, has fairly high semantic accuracy. We showed that it performs pretty well in these 2-shot prompt conditioning tests, which is kind of surprised, completely novel sets of KG relations. And there's tons of stuff to do, I think, in this area, and many other people have started doing experiments on different ways of steering a large language model like this to produce the output for a particular task.